It's all good. Okay, so any questions from last time? So, these 3 lectures are going to be unfortunately a little bit more opaque than the others, before or after. So you have to ask questions, yeah? Transform, what is, so I never talked about quasi-primary. So, okay. So what I only talked about primary fields, and the reason is, but it's, since you brought it up and it's maybe worth distinguishing. So the point is that in 2-dimensional conformal field theories, so generally speaking, I told you that the conformal group in general D dimensions is SO D, 2. It's all good? Sorry? Out of focus. Oh, okay, good. So yeah, there was some problem about that. So I mean, what I'm going to say now, as many of the questions, are not really necessary to really just get a picture of what I'm saying. But since the questions are coming up, I might answer them if it seems somewhat useful in general. So I only talked about primary fields. Okay, and the point is, primary fields are basically the natural fields under SO D, 2 in D dimensions. Okay, so those are essentially the natural fields that arise in conformal field theory in D dimensions is what is called a primary field. Okay, so if you restrict that to 2 dimensions, so D equal to 2 is in many ways special because you will then get SO 2, 2, and fields which transform naturally under SO 2, 2 are actually called quasi-primary. Okay, and the reason is that in D equal to 2, the conformal group, the full local conformal group, enhances to a bigger algebra called the Virasoro algebra. Okay, it's not SO 2, 2 is not the full, so this is sometimes called the global part of the conformal algebra, and this is called the full or local conformal algebra, and the fields that transform naturally under the Virasoro algebra is what are called primary fields, and that's a special property, are primary in 2D. Okay, so these are quasi-primary only if it is only transforming well under SO 2, 2, the global part of the conformal group. Then you say that it's quasi-primary, and the distinction between quasi-primary and primary is something that is restricted to 2 dimensions. So I only talked about primary fields because I'm not going to, even though 2-dimensional conformal field theory is a very interesting and maybe a more tractable setting to study black holes. In many ways, I think that D equal to 2 conformal field theories and the ADS3 duals of them are in many ways probably the most tractable place where we could make progress on the most difficult questions in black hole physics. Okay, so which are about finite temperature and so on. So, but I'm not going to talk about them in this course at all, even though they are in many ways many very interesting. Okay, so I just talked about SO D, 2, which is a primary field. Okay, so the fields that transform nicely under SO D, 2. So I wrote down some expression for them. You don't have to remember those expressions. So if they seem somewhat magical, just believe that there is a certain class of fields that exist in conformal field theories, which are called primaries, and if you act with derivatives on those fields, then you get what are called descendants. And the conformal, the fields in a conformal field theory are generally organized in terms of primaries and their descendants. So if you think of it in terms of like something like angular momentum representations and so on, very roughly what I'm saying is the analog of there is some state on which the special conformal transformations act and give you 0. And anything on which you act, such a state, if the same state you act with this many times, then you get its descendants. That's roughly the idea. Because K mu and P mu are both generators in the conformal group. And so this is sort of the highest weight state. Okay, so the highest weight state in the angular momentum sense. And the reason why I'm talking in the language of states is because states and operators have a natural correspondence in conformal field theory. Okay, so operators and states there is a 1-to-1 map. I'll actually show a little bit of that today because that is somewhat interesting for us. Okay, so this was sort of the mental picture that you can keep. Why the states in this conformal field theory or the fields in this conformal field theory are organized in a certain way. Okay, so the point, the why it is, etc., are not very important for us. We don't want to spend, this is the whole course of when I gave a course on ADS CFT correspondence once, which is a whole semester. We are trying to do it in 3 days. Okay, so there is a bit of stretch here. So, but I think that for the purposes that we are talking about, so this is just enough. So what I'm saying here is kind of enough. So this is so that's the. So I don't know whether I answered your question. So your question was, what was the thing? So I think
they transform in the same thing, right? Their transformation.
So for instance, when you act with d mu's on let's say you have a scalar field. Okay, so OX, OY, O1X, O2Y, 2 scalar fields. I mean, to make them look like scalars, let's call them this. And it's also important that I am computing all of these correlation functions in the vacuum. That was another question that came up. All of these I'm computing in the vacuum state of the conformal field theory. Okay, so the claim was that this basically goes, if you fix the normalizations, it basically goes as x minus y, delta 1 plus delta 2. Okay, I mean actually I wrote it as 2 delta, and I'll explain why that is. So right now I'm writing everything in sort of Euclidean kind of notation. Okay, x and y you can think of as Euclidean plane instead of Lorentzian plane. So when you have to go to Lorentzian signature, you have to do some analytic continuations, etc. And that it's important, but for the moment, it's for the things that we are talking about right now, they are not very important. Okay, so the point is that this is what I wrote. So this delta was delta 1 equal to delta 2. So only if delta 1 and delta 2 are equal in a conformal field theory, there will be non-trivial correlation functions for a scalar operator. So the point is that requires the full conformal symmetry, by the way. Okay, so full conformal symmetry means if you have Poincare invariance, you can already argue that the correlation functions have to be of this form. Okay, the function will not be fixed, but if you also have scale invariance, it will get fixed to the form delta 1 plus delta 2. If phi 1 and phi 2 have 2 different scaling dimensions. But if you have full conformal invariance, then it also forces delta to be equal to delta 1 and delta 2, so the correlations will not exist unless phi 1 and phi 2 have the same scaling dimension. Okay, so that's the sort of the logical progression of this, and all of them are easy to see. You can look at the standard reference nowadays on conformal field theory is one by Simmons-Duffin. I think it's some TASI or some lectures on conformal field theory. So you can all of these things are derived very systematically and in general dimension. So when d equal to 2, so conformal field theory is much more interesting and there is a lot more structure. So that is not covered here. But that's we don't really care about it, so this is enough for us. So anyway, so this is just from Poincare, and delta 1 plus delta if there is also scaling, and the just delta if it is full conformal invariance. So that's kind of the way in which you can remember. So to answer your question of what phi 1, phi 2, what happens to descendants, when you act with descendants, this no longer is a scalar, right? If you have derivatives acting on it, then your theory, the thing is basically it has some tensor structure. So the thing here will change accordingly. And in fact, you can derive it by just taking derivatives of this. That's it. There is nothing more to it. Okay, so yeah.
The previous lecture we had a relation between the ADS length scale and tooth coupling.
Right, yeah.
So, when we consider gauge and string theory duality, we inherently associate, keep a bound on the tooth coupling to be a strong coupling limit.
So no, so the claim of the ADS CFT correspondence is that there is a definition of so n equal to 4 super-Yang-Mills theory is defined for any value of n and lambda. So the claim is that there is certain limits in which it has a supergravity interpretation in terms of a background perturbation surrounds some ADS background, but the full definition of quantum gravity with asymptotically ADS boundary conditions is to be thought of as this gauge theory at arbitrary n and lambda. So if you want a quantum gravity, what you mean is that you want to define the theory for any value of G Newton and presumably for string length, right? So, and the claim is that you can relate there exists a definition of ADS CFT or a gravitational side of the ADS CFT duality for any value of n and lambda. But it doesn't mean that we know that what definition is for far away from the weakly curved limit of ADS. Okay, so the point is that, so note that when I wrote down, so you had two expressions of this form. One was L by L Planck to the power 4 is, sorry, it is, what is it? It's, this is one, and L by L string to the power 4 is lambda. So this power kind of keeps changes depending on dimension, some positive power, okay? So, but this was the two expressions that I wrote down. But note that I need the ADS length scale to make this statement. So, the correspondence is most cleanly defined in the limit when supergravity is, or supergravity or perturbative string theory for the second guy is better. You know, both of them are reasonably well-defined objects when you have a given background. Okay, so that's where these equations are actually best understood. But on the other hand, the claim is that there exists some suitable definition of the left-hand side which makes sense for any n and lambda. So, but that will be some quantum, completely quantum, highly non-local in the stringy sense, quantum gravity. So the fact that we have a definition of the theory, even in that setting, is what makes ADS-CFT powerful. Because then you can presumably try to understand this for some finite value of lambda and finite value of n. If you can understand the bulk description of this gauge theory, then we are working with full quantum gravity in some sense. So that's why this is called a non-perturbative definition of quantum gravity. Okay, so the point is that supergravity is so the conventional supergravity limit where the fields are roughly particle-like fluctuations corresponds to the limit where lambda is large and n is large. Okay, n is large corresponds to the fact that G Newton is small. L Planck is basically capturing G Newton. And when lambda is large, it basically means that the known locality of the string is not very visible. Okay, so lambda has to be large and n has to be large in order for us to work with standard Einstein gravity with some fields in that limit. So that's the semi-classical limit of the ADS-CFT correspondence. Is that fine? Okay, any other questions before I go on to
in the last class we wrote down some Euclidean signature metric.
Right.
And then we did a coordinate transformation, and then we wrote down the endpoint function in the G nu metric to the del nu.
Yeah, so those definitions are truly only valid for the Euclidean signature. Okay, so the point is that, I don't know what your question is, but those maps that I wrote down, when you are starting with a Euclidean plane and doing some conformal transformation to some Euclidean cylinder, those things are most easily manageable in the Euclidean signature, because there it is, the maps are completely well defined. But on the other hand, so there are, we have to worry about some subtleties when you do Wick rotations before and after. If you start with the Lorentzian signature, Minkowski space, do a Wick rotation to go to Euclidean signature, and then you do this conformal mapping to this Euclidean cylinder, and then you have to do one more Wick rotation in the new geometry in order to get the in order to get the Lorentzian cylinder. And there is some subtleties there, because the point is that it turns out that the conformal group on the Lorentzian plane is basically, there is some Z2 type factor sitting, etc. And then when you have to go to a covering. So the conformal group on the Lorentzian cylinder is the covering group of this. So there are some subtleties like that. So which you have to worry, but they are all manageable problems, and people have at least in some recent papers there are some discussions of these kinds of things. Let me not, so if that was your question, I don't want to get into it too much. Yeah.
The question was that we wrote the del nu metric at but the thing is that the metric we got had some curvature term in that also, the del.
Yeah, so that statement is valid even if delta mu nu is generalized. So that statement is valid even if, as long as it's a conformal transformation that is relating the two sides, the statement that I wrote is correct. So it doesn't matter whether it is delta mu nu. As long as your correlation function is defined on some metric, then the correlation function on the new metric, which is conformally related to the old metric, is always given by that sort of a formula.
So it doesn't matter even if the Euclidean signature metric is curved or not?
It doesn't matter. But the reason why we usually worry about delta mu nu kind of Euclidean metrics is because those are the cases where we know how to compute correlation functions. So on a general curved space, it's not always clear how one can define your correlation functions. You know what I'm saying? That's not always, most of the time correlation functions are not easy to fix. So the correlation functions, so for instance, this statement that I wrote down is basically a Minkowski space or a Euclidean space statement. So there we know how to compute various things. Conformal field theory is quite well developed, and then you can, because there are lots of symmetries. Poincare symmetry is very powerful, right? Poincare together with the conformal rescaling is what gives you all these things. But if you go to some other space where the isometries of the background are less, and you are not connected by conformal transformation to, let's say, Minkowski or Euclidean space, then you're on your own. You know what I'm saying? You can't really fix many of these things. So that's the reason why this thing and things related to this by conformal transformation are what are interesting to us. Fine? Any other questions? Okay, so if not, let me start where his question was, and I'll just say one thing, which is this statement about the state operator correspondence. Yeah. Okay, so what I wanted to say was, yeah, so because we had this observation that on Euclidean plane you could, there's a conformal transformation that, let me talk in Euclidean signature because that's where the statement is cleanest. So in Euclidean signature we could, I already said that when we were talking about path integrals, but let me repeat that, which is that let's say you have some sphere like this, and this is in Euclidean plane. Okay, Euclidean plane means Euclidean space, because we are working in general D dimensions. So the point is that you can define, so if you do a conformal transformation to go into the cylinder like this, okay, so and you want to construct the state psi living here, okay, and the way and let's say you want to construct the vacuum state as the one living here. So we know from our path integral thing that all we have to do is do an integral over all the field configurations, and then from all the way from minus infinity. The boundary condition minus infinity will not matter. Okay, so if you do that, it will decay enough, and you will basically just get the ground state. Okay, so after conformal transformation, what that basically means is that you just integrate over everywhere here. Right? So, so the way you say that is that, essentially you insert the identity operator, if you like, at the origin and integrate the path integral in the Euclidean plane, but from rho equal to 0 to 1. Okay? So this integral, this is rho, right? This is the radial direction, and this is the Euclidean plane or sphere, Euclidean space. And the claim is that because this is the path integral that gives you this, the claim here is that in order to get the ground state ground state on this shell of radius 1, which basically corresponds to t equal to 0 or tau equal to 0. Okay, because e to the rho was my tau. Right? So rho equal to so what is it? Sorry. Yeah, that's right. So yeah, so this is better. So rho equal to e to the tau basically means that I'm going from rho equal to 0 to 1 when I go from tau equals minus infinity to tau equal to 0. Right? So this is the conformal transformation that does that for me. And the claim is that then on the, this is basically the idea of what is called radial quantization. So radial quantization is that there exists, and this is possible because if you remember, I told you that you need to have, the theory has to have some symmetry under the time evolution. So that the theory, the Euclidean theory has to have some symmetry, which you then interpret as the Hamiltonian in the Euclidean language. Okay, so for instance, when we are just making a Minkowski space or whatever, this was tau and this was x. We viewed this as tau time direction because in the Euclidean space, we are assuming that the theory has some symmetry for shifts in tau direction. So here the point is that the reason why this is a reasonable construction is because rho going to rho plus some shift, tau going to tau plus some shift, which is a time evolution here, is basically just rescaling of rho. Okay, and rescalings are a symmetry of conformal field theory. So what that means is that the dilatations in the plane translates to the Hamiltonian evolution on the cylinder. Okay, so this will be an important fact / observation for us. Okay, so the dilatations on the Euclidean plane or Euclidean, I keep saying Euclidean plane, but it's Euclidean space. Okay, typically these kinds of things are, for those who are old, are done in 2 dimensions. So, but it's Euclidean space in general. Okay, so that's I think the final thing I wanted to say about conformal field theory. So the 3 things that you kind of want to take away is that the correlation functions of conformal field theories are known, at least a 2-point function, and the 3-point function also you can fix it in terms of some parameters which are called, which are also part of the data of the conformal field theory. Okay, so I told you that the spin and the scaling dimension of the conformal field theory is one set of data. So that gives me a set of possible operators in the theory. Then there is also some, the coefficients of the 3-point correlators is another piece of data. So that we will may have something to do at some point, but at least for the moment we don't need it. So the point is that in general, that is, it's believed that that data, so the set of data are basically the scaling dimensions and spins of the operators together with this extra coefficients which control the 3-point functions, which I'm not going to write down, but I just want you to know that there exists like a certain class of numbers, just like delta and s. If you give me a set of operators, it basically means delta I and si. Okay, scaling dimension and spin of the various operators, and by this operator state correspondence, because if you insert an operator here, you will get a state here in the path integral, and which is analogous to what I said here. Okay, here I inserted an identity and I got the vacuum state. If I insert an operator here, I will get a corresponding state here. So this is essentially the operator state correspondence in conformal field theory. So I can insert a local operator here in my path integral before I do my integral of this type. So this 0 stands for the fact that I'm putting it in the origin here, and this basically defines for me some state psi, if you like. Okay, so I'm being slightly heuristic, but these are all things we have done before. Okay, so heuristic because I'm not putting boundary conditions, I should put a ket here, etc., etc. But this is schematically, this is what it is. Okay, so so this corresponds. Sorry, let me call it O actually, because I'm inserting this O. So this is essentially the state operator correspondence, and all the things, the only things I'm actually saying about conformal field theory today, except for when the questions come, are all in Harlow's lectures. I'm following Harlow so that you have a place to go and look. Okay, so but he doesn't emphasize this parameters and so on, but there are some things I'm emphasizing slightly differently, so roughly these kinds of statements are there, so you can go take a look. Okay, so what I wanted to say was that in order to specify a conformal field theory, you basically just need the set of operators, local operators in the theory, which are controlled by the scaling dimension and the spin of the field, and the 3-point correlation functions of every possible field in the theory. That's also another set of data. So the claim is that if you give me these sets of data, not all sets of such data are consistent. Okay, so one can argue that they are not consistent, but there exists a consistent choice of such data, and this defines the conformal field theory completely. All the higher point functions can be written in terms of these. Okay, so this is what makes conformal field theory very powerful. And this idea that you can write down everything in terms of this thing is, I'm not explaining why, but it's not a difficult fact. But the point is that let me just say one thing, which is that not all such choices are consistent. So, but the correlation functions of higher point fields can put consistency conditions on them. Okay, and because of the claim and the belief, this kind of a folklore is that all consistent conformal field theories can be completely fixed using the constraints arising from the higher point correlation functions on the fields of the theory, and that fixes not just delta I and s, and that not just that does fix all the higher point correlation functions, but it also tells you which choices of delta s and Cijk are acceptable. So it's generally believed that the consistency conditions are sufficient to completely fix the space of all conformal field theories, even though there is no proof or anything for that statement. And that idea is sometimes called the bootstrap. So because the demand of consistency condition fixes the data that defines the theory as well. Okay, so that's the reason why it's like a back and forth aspect to it. So you plug in this data and you compute the correlation functions, and the correlation functions are going to completely, the consistency of the correlation functions coming from general principles of quantum field theory will force you to fix these things completely. And this is what the bootstrap idea is. Anyway, so this is kind of like a complete, general story that as far as we need for conformal field theory. Okay, any questions? Okay, so now let's go on to how we are going to, so we need to talk about when is a semiclassical limit well defined. So essentially the semi-classical limit basically means that n and lambda are large. Okay, so at least for n equal for superangles theory. But we would like to understand for general conformal field theories, what kind of conditions should one expect? Okay?
Does this spin has anything to do with the usual spin of theories?
Yes, yes, it is because it is, this is basically coming from the fact that the spin of the, conformal field theory is, conformal group is a bigger group containing Poincare group, right? So the what is it called, the generators, so or the charges that specify the symmetries or the representations of the various fields contain spin. So this is just the Lorentz spin, that's exactly what it is. And then, so for instance, for a scalar field, this S will be 0, and it will only be specified by delta. But there can exist whole spectrum of fields which have various properties. So, in some sense, what one means by quantum gravity now in ADS would be that what kind of theories, so the semi-classical limit of quantum gravity, when does it exist? So, when does an Einstein gravity description of the bulk exist? When does that exist? So roughly speaking, we will say that that is when there is a number of, the theory has to have a free parameter which we call n, and various statements can be made about the spectrum of the theory and how correlators work for large values of n. So this is the idea. Okay, so so basically the theory should come as parametric families of theories. And that parameter is basically what we call n. And this parameter is, so let me write down some general expectations of when a CFT when a CFT has a bulk semi-classical limit. Semi-classical holographic description. So this is, it's not fully known when this is the case. We don't really know when a conformal field theory has a completely, we don't know the full set of demands that one should make. But these are sort of the general, what I'm going to write down now are the things that one generally expects. And roughly speaking, they come from the expectation that, in theories of gravity that we are familiar with, including in the n equal 4 superangles case. Note that I'm jumping off from n equal 4 superangles and trying to make a general statement about ADS CFT. Okay? So in n equal 4 superangles, there is a small number of fields which correspond to fluctuations around the gravitational background. So fluctuations around ADS. Essentially they are basically what are called the supergravity fields. So I wrote down an action, if you remember, which was roughly of this form, right? Minus some f square, some scalars, etc. Okay, so there is a structure like that. Note that that's a very small number of fields. String theory has a huge number of fields, huge tower of massive fields. And this is basically like if you look at the spectrum of fields in this theory. So this is what are the fields that we have is the question. So and the general expectation is that these the first expectation is that there should exist a number n which controls. So let me write it down. So there exists a parameter n such that large n corresponds to, large n has the interpretation as G Newton going to 0. Okay? So, and the idea is that there exists a set of primary operators whose scaling dimensions delta I do not scale with n. Okay? So what that means is that for any value of n, the number of light fields in the theory is small. That's what it basically means. So the reason is that you kind of think of this as this, the fluctuations around the gravitational background are small. Even though, so the idea is that n went to infinity, G Newton is very small, and so in general, in a gauge theory with SUN gauge group, there will be a huge number of operators that you could write down. Okay? But the claim is that there only exists a small number of operators with small scaling dimension. Okay? And these small scaling dimension operators are what get interpreted as the bulk gravitational fluctuations or the bulk fields living on an ADS background. Okay? So this is the first bit of the story. First bit of the story. We can motivate it at various levels, but let me just write down the statements and then we can try to get some let's say intuition for it.
Do you mean these two statements are
No, I'm not saying that. So, yeah. So, no, I'm not saying that. So, yeah, I'm not saying that. I'm just saying that I'm making a list of things, which are kind of related. Some of them are actually, can be derived partially from the others, etc. But, yeah, so a finite number of single trace. So, yeah, single trace is a word I will not define, but so these small fluctuations that I talked about in the gravitational side, that's what people, on the gauge theory side, we think of them as single trace operators. Okay, so I will say why, so these are the kind of things that make explaining this without saying anything a little bit harder, but single trace primaries with spin less than or equal to 2. So that's essentially what we are doing, is we are just taking it from supergravity here. Okay, in supergravity, these fields, all scalars have spin 0, spin 1, and metric is the highest thing. So that is spin 2. So we are claiming that this is a general feature. Okay, so we can only have, so if these guys are dual to single trace primaries in the gauge theory side, then the idea is that there is only this many, there is not many more. Okay? So there is a slight complication to this when there are these compact S5 like spaces, but this is good enough. Is that okay? I see many puzzled faces, but we can,
So for the first point, for these very small number of fields, this delta I doesn't scale with n. Is that the?
Yeah, so exactly, that's right. So these fields, so those are the fields for which the dimensions, scaling dimensions are not scaling with n. So it could be the case that there is, well, I mean, there are fields in the theory which have high scaling dimension. Okay, but the statement is that there exists a small number of these low-lying primaries which have a natural interpretation as the gravitational fluctuations around fixed backgrounds. And the expectation is that that's what essentially all that we are made of. Because the scales which we are operating are all low energy effective field theory kind of stuff, and so the mass scales involved are not the string scale or the Planck scale. Okay, so that's what roughly speaking it means. So
is there any such statement for spin I or CIJ?
there are various statements, but I will not make any of them. There are various statements, so there are various statements about how CIJ should go in theories which have black holes. So I am very specifically talking about some of the properties that we expect in theories which have Einstein gravity duals. That's what I'm really talking about. Okay, so if you relax this, there are various things one can do. I mean, yeah. So I mean, as I said, at some level, for an arbitrary n and lambda, the theory is basically dual to some arbitrary quantum gravity. Right? In the bulk description, we don't have any real connection with. So the interesting, or the reason why this is of utility is because in the large n limit, when G Newton is small, we expect that we can understand this in terms of this large n gauge theory. So that's why there is, we can match things. Then we can check, and that's one of the checks of ADS CFT correspondence.
So we're saying that there will be single trace operators spin greater than 3, greater than 2.
There can be single trace operators spin greater than 2, but
Spin up to 2, we know what each spin responds to, like.
in the bulk, you mean? Yeah.
Like graviton.
Yeah.
But what would?
So those will basically be states that correspond live in the spectrum of the string. So this is just basically the lowest lying part of the string spectrum is what we call gravity. So, but there are higher lying states. Okay, so it's a little bit easier to talk about these things once in the case of supersymmetric theories, because there is a notion of a chiral primary and there is a notion of a non-chiral primary. Okay, so the chiral primary states are what are dual to the supergravity states. In the n equal 4 superangles, for instance, that's the thing that one can explicitly check, for example. So chiral primary come from, it's basically a constraint that involves not just the conformal descendants, but also a statement about supersymmetry. So there is a condition coming from the supercharges also. So it's a little bit easier to make that statement because it's cleaner in some ways. Because I would say that these states, the states that come from supergravity, are basically what fall into what are called the chiral primary operators of the n equal 4 theory. Okay, but the non-chiral primaries can live in all these higher string states as well. So so that's sort of the match. And that's how in fact the chirality condition is precisely related to the spin less than 2 condition. It's very directly related to it. Okay, so if spin is that's it's not very important for us. So let me not get into that. If you want, you can ask me later. It's not very complicated, but it's a kind of a distraction. Okay, so another important thing. So the spin 2 field, spin 2 guy is dual on the gauge theory side or the CFT side to the stress tensor. And it is unique. Okay, it's related to the fact that the metric is unique, and it's related to the fact that CFTs have a unique stress tensor. So that's already so all of these things that I'm saying, the fact that they kind of work are, sort of circumstantial evidence for radius safety in some sense. Because none of these statements would have worked otherwise. Okay, so the CFTs have a stress tensor, so that's dual to the metric on the gravity side. Okay.
So what is this string, the single trace?
Single trace essentially, so in a general conformal field theory, single trace doesn't really make any sense actually. But what it makes sense is when you have these gauge theories, right? A general conformal field theory in principle does not need to be a gauge theory. But for instance, in the case of these large and gauge theories, which happen to be conformal field theories, like n equal to 4 superangles theory, there is a natural notion of single trace, because the fields in the theory, if you want to make gauge invariant local operators, what you should do is basically construct operators of this form. Okay, so the n equal 4 superangles theory, so let me just write a few things. So contains 6 real scalars and some complex fermions. Let me call it alpha, like this I write it, and then there is a gauge field A mu. Okay, so these are the fields in the theory. So these, and the point is that, let's say you write down a gauge invariant operator of this form. This is by construction gauge invariant. So single trace basically means that those gauge invariant operators which are constructed from single traces. So in principle, you could also take a trace of something and multiply by another trace. Right? So this is called a double trace operator. Okay, so the reason why we care about this is again kind of related to this chiral primary thing that I mentioned earlier, is that these kinds of operators are the ones, so to answer your question most straightforwardly, there is no, there is no direct definition of what single trace means in a general conformal field theory. There isn't, but there exists classes of operators which satisfy the properties that I'm going to list. That's a better way to think about it in general conformal field theories. But for single trace operators in these large and gauge theories like superangles theory, you can actually show that these properties are satisfied. So that's the reason why we define them. Okay, but so that's also one reason why I did not want to define single trace, because it's not very important. The existence of a certain class of operators which satisfy the list of properties that I'm talking about here is what gives you the interpretation that those operators are dual to the small fluctuations around fixed backgrounds in gravity. So that's the picture, okay? So, and you should also know that many of these things are, the full ADS CFT correspondence, the dictionary is not completely done yet. In many ways, ADS CFT, even though people might think that it has been around for 20 years, I think we have only scratched the surface. You know what I'm saying? There is, the most interesting questions of quantum gravity are still, there is a sense in which it is still quite wide open. Okay, so So many of these statements that we are making are somewhat conjectural, but we have, quite a bit of confidence in these things, many of them. But it should be emphasized that it's really a conjecture. Okay. So if we normalize the 2-point function such that, like when I wrote down of the single trace primaries, let's say you wrote down this phi are fixed so that this was of this form. Okay? Where there is this normalization. This normalization is not fixed by this conformal symmetry, because that can be arbitrary. So if we choose it, so choosing this to be 1 is a choice of normalization for my scalar field. Okay? And if I choose it to be like that, if you normalize the 2-point function without a factor of n, in other words, factor of n, in other words, this is basically 1 and not some n dependent ugly function. Okay? If you choose it to be that, then the higher point functions are suppressed. Well, I mean, maybe I should say, then the 3-point function is suppressed as 1 over n. Okay? So there will be a factor of 1 over n in my 3-point function. Fine? Yeah, and this is something that I've already mentioned to you once before. So I used the word single trace operator already probably before. Right? Or maybe I said, so the single trace, yeah. So another phrase for it, which is maybe more generally applicable, is generalized free field. So these both words mean the same thing in a general conformal field theory. Okay? Generalized free field. In a general large N conformal field theory. A conformal field theory which admits a parameter n which can be taken to be large, the word single trace essentially means the same thing as generalized free field.
So you talked about primary fields there, but
yeah.
Premium is not primary.
So you mean like the 2-point function is not x minus y? That's what you mean? What is the statement?
I mean, that statement is not primary, right? Single trace primaries with spin less than equals to 2.
Single trace primary, yeah, so I think that, it doesn't have to be here. I think that, so let me just say single trace operators if you want to make it a little bit more general. So you're unhappy with the fact that this is somehow constructed from some 2-point function involving scalar or something like that? Is that what you're worried about?
I mean, T mu is not a primary field, right?
So okay, that's true. I mean, I just want to have some low dimension fields which are single trace. That's all I want. Fair enough. Any other questions? Yeah, any other questions? So I have one more statement and then we are done. And that, well, actually 2 more statements. The next statement is something that you've already seen. So which is that if you take n-point correlation functions of these single trace operators, they satisfy Wick's theorem up to 1 over n corrections. Okay? So that's roughly the idea that you have fluctuations in the gravitational background which act like free fields. So the corrections are going to be in 1 over g, or sorry, in g, which is basically the idea that it's suppressed by 1 over n. Okay? So yeah, so this I will just n-point correlators factorize. So factorization is just another word for this factorize. Factorize basically just means it satisfies Wick's theorem. Wick's theorem, but not with the constraint that the 2-point function is that of a free theory. That's an important point. Okay? So it is, Wick's theorem is satisfied, but the 2-point function, unlike in the case of familiar Feynman diagrams, is not that of a free theory, because the 2-point function is of some strongly interacting conformal field theory. Okay? So that's, so the final statement I'll make, which is again sort of a general observation, is that that's exactly Wick's theorem. That's what factorization means. Wick's theorem is if you take odd number of odd number correlators it will basically give you 0, and up to order 1 over n corrections. So that's consistent with what I wrote here. So 3-point function is suppressed by order 1 over n, right? But the 4-point function will be a sum of products of 2-point functions. That's what Wick's theorem is. Up to, again, order 1 over n corrections. So that's what factorization means. Okay? So factorization means precisely Wick's theorem. Up to 1 over n corrections. Okay, so
Order 1 correlation should keep 0, but 3-point, we can fix the form of 3-point function.
yeah, but the 3-point function will be in terms of, but the CIJKs are not known, right? CIJKs are arbitrary. So the statement is that the CIJKs have to run, have to be suppressed by a 1 over n. That's what this means. So if, so if you have OX, OY, OZ, expectation value in the vacuum, in a conformal field theory, it will basically take some form like this. And Z minus X to various some combination of this has, so let me write less delta here. All of them are delta, delta, delta. Okay? So then, so this basically will give me, so this is a general formula in conformal field theory. So what I'm saying is that this CIJK will be suppressed by a factor of n. So note that the 2-point function was not suppressed by a factor of n. 2-point function was normalized to 1. So then the statement is that the 3-point function is suppressed by a factor of n. So this is one of the expectations that we have for conformal field theories which are holographic. Okay? And this is a more general version of it, which is that in higher point correlation functions, odd guys always are suppressed, but even guys factorize in the sense of Wick's theorem. Okay, so yeah, so that I think is, there are many other statements I could make, but let me just, so one more thing I will say is that black holes in theories with black holes, the expectation is that, in theories with black holes, the expectation is that those corresponds to the parts of the spectrum which is has energy of this type. Energy that scales. Let me call it, so to make it concrete, let me call it n square, because that's what it happens in n equal 4 superangles theory. Okay? So the idea here is that the reason, why am I saying that? The reason I'm saying that is because G goes as 1 over n square. So all the equation that I wrote down, L by L Planck is equal to, to some power is n. That's really the statement that G is 1 over n square. Okay? So, yeah, so, and, so the point would be that the reason why this has to scale as order n square is because only then it will back react sufficiently to create a black hole or a curved space-time, or something that is not ADS. That's what it really means. So, if you remember, we needed Gm to be some Schwarzschild radius, right? So, and G goes as 1 by n square is what we are saying. So M is basically energy of the state. So if E is not scaling with n square, this RS will not be order 1. We want some macroscopic horizon, then it must necessarily be the case that the energy of the state that you're looking at should basically scale as n square. N square or some positive power of n depending on the theory. Okay? So this is another very important fact, and this will be very important for us for all the black hole discussions. Okay? So there is one slight subtlety here which I will talk about. Everything has subtlety, so there is no free lunch. So the point is that this is true for what are called large ADS black holes. Okay, so there are black holes that are stable. They can really be thought of as stable states in the conformal field theory. Because the large black holes, so ADS, if you remember, is like a box. I'll say this again, but it's good to hear it once already. So if the black hole is big and its radius is bigger than the length scale of ADS, a big black hole, even if it radiates, it will reflect back into the horizon and it will stay stable. Okay, so such black holes are called large ADS black holes, as opposed to small black holes which live here and they are somehow small, and they just, if you wait long enough, they'll just evaporate completely into just radiation in the system. Okay, so these are small ADS black holes and these are large ADS black holes, and these are not eigenstates of the conformal field theory because they evaporate away. These, on the other hand, the microstates of this black hole can actually be eigenstates of the theory because they don't evaporate. They are stable. They just sit there. If you time evolve, they will always be there in the Hilbert space. If you start with a state which contains a large black hole, it will always be there in the system. Okay, so that's what this. That's why this statement is really for large ADS black holes. So, and the claim is that most of the states, there will be some low energy fluff like the single trace fluctuations, and maybe in some theories, generally in string theory you will also expect some fluctuations coming from the strings, excitations of the string, but they're all basically low energy fluctuations. So, but at the very high end of the spectrum, very high end means energy scales of order n square, where we have no real way of tracking the string theory on the bulk side. We have no understanding. We can write down this solution in the supergravity as as a metric, as a Schwarzschild and so on, but we don't have any stringy direct understanding of black holes, in this regime. Okay, so in this regime we don't have a direct understanding, but from the CFT side we expect that they should go like this in the energy. Okay, so these are the large ADS black holes, and they will be a very important player in the rest of our discussion. So yeah, and there is a gap. So that's the thing that I forgot to mention. So there is a gap in the spectrum. So all the low-lying guys, which are not scaling with n. So note that all of these guys, the statement here is precisely that there exists a few low-lying excitations in the Hilbert space which do not have energies. Delta, I remember by the cylinder map, I said that the scaling dimensions translates the energy of the state. Right? So the scaling dilatation became the Hamiltonian on the cylinder. So the scaling dimension is just the energy of the state on the cylinder. So this energy is small in units of n. If your units are in the scaling with n. So these states are light states, and then there is these heavy, horrendous, humongous states which correspond to black hole microstates. Okay, so note that on the CFT side, the black holes, they are individual states, and we expect it to be extremely densely spaced. These are highly complicated theories. Okay, so these are highly complicated theories with very dense spacing of levels, and that dense spacing is what gives rise to black hole entropy. Okay, so so this what I said here does not immediately tell you that the spacing is dense. This is a separate statement what I just made. So but that is, we expect that, and it's in these conformal theories that we're talking about are very complicated theories. We don't know how to solve them, especially at finite n. In the large n limit we have some tricks for solving for scaling dimensions and all that, but that's for, if you're really interested in black holes, they are of, at least so far I don't think they have not delivered anything very useful. So the theory has the amazing thing about n equal for super EM theory is it's also an extremely symmetric theory. Right? It's an extremely symmetric theory, but it has these states which are black holes, which are high-lying, which break all those symmetries and are not really accessible. So, but because of the symmetry of the theory, there are various regimes in which the super Yang-Mills theory has been solved in some sense. We can exactly solve them, but typically those regimes are always places which avoid black holes. You know what I'm saying? So it's like, or at least these black holes I'm really talking about are the real target. If you understand them, these black holes, and also there is these small black holes, because this one is stable and this one is evaporating. So if you understand these two black holes in ADS-CFT, we have understood black holes in flat space as well. There is nothing in flat space. So this is basically like a flat space black hole. Right, because it is just sitting there as a small, the length scale that is relevant here is L, which is this radius of the horizon is much smaller than the length scale of ADS. So which means that as far as a black hole is considered, it's not sensitive to the curvature of the space. So it's essentially a flat space black hole. And just like a flat space black hole, it can evaporate away. So this black hole on the other hand is an intermediate step in some sense, because it is a black hole which is eternal. And this is in some sense the real location for the eternal black hole. In flat space, people can write down this eternal black hole metrics, but they are not really meaningful because we know that Hawking radiation exists, and after some time scale it will evaporate away. Right? So it's not eternal black hole. Penrose diagrams are just a fiction in flat space. But here you can actually write down eternal black holes, and we expect them to be eternal, because they are not going to evaporate. They are going to sit there. So understanding them is some sort of like a God-given intermediate step in understanding the, let's say this black hole. And it's not completely clear whether, I do think that understanding this is a good step towards this, even though it's probably not completely sufficient. Okay, so this is the small black hole and this is the big black hole, and if we understand them, we understand all these things. So, but also you might have heard various things about supersymmetric black holes and counting, entropy and or so on. So note that none of those supersymmetric black holes are always at 0 temperature. So they don't really address the mainstay questions of information paradox in quite in the way that we want them to. So they are good for understanding entropy counting questions, but not the most difficult questions, like the question of the smoothness of the horizon or information paradox, etc., etc. Okay, so any questions? So I'll just make the statement about the ADS CFT correspondence. Yeah, I have perfectly exactly enough time. So any questions on this? And I think we are, so that will conclude our sort of 3-day summary of ADS CFT. So I think that, the yesterday's class, I think I tried to kind of unnecessarily explain what a primary field was a little too much, instead of just telling you to believe it, which would have made you at least, more comfortable, I think, because if sometimes, explaining something is actually counterproductive to understanding something sometimes. So I think that, other than that, I think, I think that, so I think today's summary of conformal field theory, I liked it better, because I think it was more at the level of a story, and that's all we need. I got somehow sidetracked into that. So for the black hole purposes, this is all we need. Okay, so
understanding this intermediate step is from the bulk side?
Which intermediate step?
The large black hole,
so that's an interesting question. So we don't understand it neither from the bulk side nor the boundary side. But in order to, I think the bulk questions are harder. Because the bulk questions, typically we don't even understand what the so note that at finite n and finite lambda, at least in principle, we know what the theory is. We have a Lagrangian we can write down. In principle, if we had, if we could do, Euclidean, path integrals with fermions, which is not, it's not an easy task, but at least in principle, it is, that's something that one can put on a computer, etc. We can try. Okay, there are at least some sense in which people have made progress on these kinds of questions. So, but understanding the question of what, like for instance, an observer would see from the bulk is a much harder question, because it's not, the kind of observables that are accessible to us in ADS CFT are generally speaking boundary correlators. Boundary correlators means the CFT that is living at the boundary, because this gauge invariant operators, at least in principle, they are well defined. In the bulk, we don't really know what bulk local measurements, etc. mean. Those are much more difficult questions, because there is always one has to worry about diffeomorphism invariance, because the true observables of this theory are somehow living only at the boundary. So somehow we are asking these questions about, infall or black hole, etc. So those questions will have to be phrased in some sense in a relational way between what the observer and the infaller are seeing, and so on and so forth. These are all complicated questions which kind of cuts to the foundations of quantum mechanics also. So everything is up for grabs there. So those are questions which are difficult. So but on the CFT side, I think it will be interesting but not fundamentally very useful. Fundamentally useful for understanding the flat space black holes, at least bulk ideas aspect of flat space black holes, to understand what these states look like in the CFT. Okay, so there is a regime in which we know we can fix the regime of n and lambda in which small black holes should exist. Let's say the spectrum energy of the state is between this particular n and lambda, n, some function of n and lambda, and n square. Okay, so I think it is, I forget what exactly it was. It's basically something like n square by, it might be some power less than, e less than n square, where you have to put in the ADS length scale to make everything correct dimension. But once you do that, in this regime is where we expect the small black hole to exist in the CFT. Okay, so and above this energy is what this is true, and this is what I'm emphasizing here. Okay, so so from the CFT side, I think it may be possible to do it, and people have put these things on lattices. At least simpler versions of n equal to 4 superangles theory. So simpler versions means there is like lower dimensional versions of such theories, which correspond to other gauge gravity dual systems, where people have actually put that in, and then you can compute some of these thermal aspects. You actually see from the gauge theory supergravity predictions coming out, and these are not protected results like supersymmetry. So this is like I would say that that's probably the strongest check of ADS CFT correspondence, because it really cannot be, it's a remarkable test, but it's only done on computers. So so I think that so that part is, this is actually quite interesting and quite exciting part in some ways, because it is really like at the most cutting edge of what we don't understand. I mean, it's kind of facetious to say it is cutting edge, because I would say that the knowledge about these states has been sort of, we have not really progressed in our understanding, especially of the small black hole in the last 20 years. Okay, so ever since ADS-CFT came, for instance, if there is a standard review of ADS-CFT for people of my generation, which is called Magoo. So this is the man himself. This is Aharoni, Gabsar, Uguri, and Oz. So in non-alphabetic order. So, and this is a review of ADS-CFT correspondence. So there is some discussion of the small black hole there, and there has been some progress in constructing the small black hole in ADS n equal to 4 superangles theory, or in the bulk side, ADS 5 times S5. That has been done. People have constructed numerically small black hole solutions in ADS 5 times S5. That has been done, but I would still say that the understanding is essentially where it was at the level of this review. I don't think it has progressed much more than that, even though there are directions that are kind of promising. Okay, so so now I want to say what the ADS-CFT correspondence is. So this is about the structure of the theories on both sides, and what we expect from a conformal field theory which has a semi-classical dual. That's what I said here, and this is important for us because we care about black holes and which states correspond, etc. But there is a more basic, and the initial discussions of ADS-CFT correspondence right after Maldaceno's conjecture were about building the dictionary. So what in ADS you do something, at least in the gravity limit, not in the full string limit we don't have an understanding. So in the gravity limit, what happens for the correspondence? Okay, so the expectations, the ADS, so let me call this the ADS-CFT dictionary. So there are many pieces in the dictionary, and I'm just going to talk about the most basic ones. So the first idea is that the Hilbert spaces on both sides are the same. This is sort of obvious, or same. So it is sort of obvious, but it's an important statement to understand clearly. So note that, so let me draw a picture here. So this is your bulk theory, and on the boundary there is some other theory living. Okay, note that if you're thinking of gauge theory living on the boundary, the gauge invariant observables are what constitute the, acting on the vacuum state, are basically what constitute the Hilbert space. So on the boundary, we want SUN invariant operators, CFT side. So this is on the CFT side. And on the bulk, at least in the gravitational limit, we want diffeomorphism invariant observables. In other words, coordinate invariant observables. So integrals over all of space-time. Okay? So diffeomorphism invariant operators. So these are the operators on both sides. The claim of, so note that this statement is only really, we can only make them only in the gravity limit of string theory. In the full string theory has a much bigger gauge invariance and diffeomorphisms. We don't fully understand what it is, but generally speaking, it's there are these things called higher spin symmetries and all that. Okay, but the full symmetry of full gauge invariance of string theory is not known. So this is what we expect in the gravitational limit already, and we expect that whatever be the gauge invariance on the bulk side, if we construct the gauge invariant operators on the bulk side, they should match with the SUN invariant operators on the gauge theory side. So that's the real statement. Okay, because I'm making this in terms of Hilbert spaces, but note that it is a CFT, so it's again state operator correspondence. So you can make the statement in terms of states or in terms of operators. Okay, so so that's the first observation, and then the second one is already something that we checked. In fact, we used it in various cases. So there is an SO d(2) symmetry on both sides. The theory has conformal invariance on in the boundary, and the quantum gravity in ADS background, we expect it to have SO d(2) symmetry. And the ground state ADS has that symmetry. So note that, of course, for specific realizations of ADS-CFT correspondence, the symmetry can be bigger. For instance, for the ADS 5 times S5, n equal 4 superangles, the symmetry is actually bigger than this. Because there are supersymmetries, conformal symmetries, supersymmetries, there are extra supersymmetries and super conformal symmetries, etc. that also match. So that's also a check. So, but I'm saying that for the minimal bare bones ADS-CFT correspondence, that symmetry should be the same on both sides. Okay? Yeah. Yeah. So finally, so this sort of the final, so what really is sometimes called the ADS CFT correspondence, which is really a statement about so I'm thinking of a scalar field living in the bulk of ADS, but this statement is not just restricted to scalar fields. Okay, so any of these low-lying fluctuations that I mentioned, this should correspond to some field of scaling dimension delta on the CFT side. Okay, so the idea is that note that bulk operators, localized bulk operators don't really mean anything because they are not diff invariant. But boundary values of bulk operators do mean something. And if you take a scalar field of mass m, this is basically another famous formula, if you like. And the way you get it is by solving the bulk scalar field equation and all that. I will show you. Actually, this one I think I'll show you in a second how to get it. Okay, so the statement is that these two things are the same. So if you take the bulk value of a scalar field of some mass m, that corresponds in the boundary theory to some operator which is of this form. Okay, so yeah, there is a couple of caveats which we will emphasize as we go. So note that this is also this statement is really for fields which are Lorentzian ADS CFT correspondence. This statement is really for Lorentzian ADS. So it's really the ADS that we are really interested in for black hole purposes and all that. Okay, so yeah, so how does that translate? So one of the ways in which you can motivate this, okay, is to so we can solve the bulk scalar field wave equation. Let's say we have a scalar field phi, okay, and we solve for the bulk scalar field, in the ADS background. You remember the metric that I wrote down, which was minus 1 plus r square by L square. So this is my ADS metric. It's the global ADS. That's where I'm working with. Okay, so this is my ADS d plus 1, and I can solve my scalar field in this background. Okay, so write down the wave equation and then solve for the scalar field. And then there will be, because it's a second order differential equation, it will have two solutions. Okay, so one solution which will basically blow up at infinity, very roughly speaking, and another one which can actually be, which has finite energy. In the sense that if you compute the Hamiltonian for that, for that mode, you will find that it is finite energy. And such modes that mode is called the normalizable mode. So so the phi, because it's a second order wave equation that you're going to solve for, you will basically get two modes. One is called the non-normalizable mode, which we will not care about, and we'll always set it to 0 for this course. And then there will be the normalizable mode, which has finite energy. If you compute the Hamiltonian, if you have a scalar field Lagrangian, you can compute its Hamiltonian. And that Hamiltonian will be an integral on the spatial slice. And that integral will be finite for that normalizable mode. Okay, for this guy it will not be. Note that I am working in Lorentzian signature. Things are, sometimes ADS CFT, the first version of ADS CFT was in Euclidean signature. So this is I'm talking specifically about Lorentzian signature. So this we will set to 0. Of the two independent solutions, this guy we will set to 0, and this is the mode that I'm going to compute. Okay, this is the mode that I'm going to consider. And with this mode, after normalizing it properly, I can basically compute this quantity, this time ordered phi of t r omega, phi of t prime r prime omega prime on the vacuum. So this is just a bulk quantum field theory in ADS calculation. This is something that we know how to do. Okay? So this is the time ordered correlation in the bulk of ADS. Okay, and this is explicitly doable because the wave equation in ADS, you can solve it in terms of hypergeometric functions. I'm not going to do all those steps. These are all, in principle, if you want to really pursue it, you have to do those things. Okay, it's worthwhile. So if you compute it, you will basically find that there is some hypergeometric function that you get, and this is explicitly calculable in terms of hypergeometric functions. Okay, and I'm not going to write down that expression, but there exists some expression. Some complicated and hypergeometric stuff, but now I can do this. Okay, I can compute limit r and r prime going to infinity, r to the delta and r prime to the delta. Okay, so basically I'm taking the boundary limit of this correlation function. So note that this is a bulk 2-point correlation function because there is r also here, and I'm taking the boundary limit of it, and the claim is that this basically gives me the 2-point correlation function of the CFT, time order 2-point correlation function on the cylinder. Okay, so this is the final answer. So this is sort of, you can think of it, this is an explicit calculation that you can do, and the final result is a 2-point correlation function of a conformal field theory on the cylinder. Okay, it's not a very easy calculation to do because of this I epsilons. You have to be careful. It's not a super easy calculation, but and there are some technical complications, but fundamentally it is something that you can look up in a book. Okay. So, and at the end of it, this is if you want, this is kind of a check of the duality as well as this particular prescription. Okay, so note that, so the reason to believe the correspondence at this, in the sense that we are talking about here, that is only slowly that you can build that sort of intuition. So here it might seem like I just pulled it out of a hat, right? I gave you a prescription for why this should go like this. Okay, so one way to motivate it, one partial motivation for it, and there are many. There is, the semi-classical level, the correspondence has been checked very thoroughly. Okay, so, but this is sort of the most basic check. So on a cylinder, this is the form of the 2-point correlation function, which actually you can again derive from what I told you about the correlation function on the plane. By doing this conformal transformation or scaling transformation that I said, right? You can actually derive this. Okay, so because I wrote down the Lorentzian correlation function on the plane, and I told you how, if you go to go to a cylinder, how exactly it transforms. So you can put these things together, not completely trivially, but it's possible to reconstruct all of these things. Okay, so this is the sort of the most well-known sort of ingredient of the ADS CFT correspondence in that sense, and I think so what is the time? Yeah, so final thing. So a similar statement, I'll emphasize one particular case, which is r to the d g mu nu, which is the metric tr omega is t mu nu r omega, t omega on the cylinder. Okay, so this is r going to infinity. This is because the stress tensor has scaling dimension delta equal to d, where d is the dimension of the space. Okay, so this is this entry is there for all ADS CFT correspondence examples. So is there any questions, or are you completely destroyed? I think I will stop here, but I think it's good to ask maybe I don't know, some questions just to make me feel better. So I think so let me kind of recap. So where did we go? So we started with conformal field theories. So the only thing you really kind of need to know is that there exists a special class of fields called primary fields, and their correlation functions are known. okay, an explicit form. And we can go from planar conformal field theory to cylinder conformal field theory. So those are the 3 facts that we need as far as ADS CFT is considered. And then what we did was we said that, okay, there exists a special class of simple operators in the conformal field theory which correspond to small fluctuations around the ADS background. So those are what we call single trace operators or generalized free fields. So that's one set. And then and their correlation functions factorize. Okay? So as long as the number of operators that you're inserting are not too high. So if you put in exponentially large e to the n number of operators, for instance, they will back react, or even large n, if you put it, they will back react. Right? Because a scalar field has some, so if you put many scalar fields, the scaling dimension is roughly speaking adding up. So if you have a scaling dimension of n operators and n times delta is basically, or n square operators, then that has enough energy to form a black hole, right? So that will back react. So when we say that correlation functions back react, that's a low-lying statement in the spectrum. Okay, and that's one. And then there is the third important point in the discussion of the spectrum is that there exist these high-lying states which correspond to black hole microstates, which are of energy order n square. Okay. So, and that was basically what that was about and then there is a gap in the spectrum. The low-lying part is somehow, it's somehow sparsely populated. That's the belief. And then there is the high-lying part. Black hole microstates are very dense because they have to reproduce the black hole entropy. And then, so that was kind of like the rough structure of the spectrum of ADS CFT. And then we described the ADS CFT correspondence, the most well-known ingredient, which is that if you have a bulk field, by taking its boundary limit, we can construct CFT operators. Okay? So I think that's kind of the full story. I don't think there is,
Can you just give a definition of microstate and black hole?
Yeah, so black hole microstate basically means that, if you, in classical or semi-classical gravity, black holes' horizons have entropy. Right? So that means that if you want to think of them as genuine quantum mechanical systems, you have to give them, there is a microstate is basically something that does not carry entropy. That's what it means. So it's basically if you have like the air in this room has entropy. So what you do is you describe it in terms of each individual molecular configuration, then that's a microstate. That does not have entropy. So in the same sense, if you have a black hole, the black hole is a coarse-grained or approximate description for any of the microstates that fall within the let's say the microcanonical sliver. So let me write down the CFT spectrum as a picture. So I mean the part of the spectrum that is important for so this is energy, and so this is like this is basically order 1 energy, this is basically order n square energy, and so here the states are roughly speaking spaced order 1. Okay, here on the other hand we expect that there is a huge dense quasi continuum of states, and the reason is, so you expect that the level spacing here is e to the minus n, or e to the minus order n square. Okay, so because the point is that that's the way in which entropy is counted is that you have so what you mean by a black hole is basically a very small order 1 window, if you like, of energy. Okay, so there is a set of microstates in the CFT, and there is an order 1 sliver here. That's a microcanonical sliver. Right? So in that microcanonical sliver, that's the resolution that we have in classical gravity. So if you look at something with energy which is small, some small amount of energy, there is a humongous number of degrees of states in that small window. So so each of those states is what we are calling the black hole microstate. Okay, so essentially if you wanted to compute entropy, you define k log omega or whatever, right? So this omega, everything that goes into this omega is a microstate. So in this case, if you have a small sliver of energy, so this omega will be the number of states in that sliver. Okay, so that's basically a black hole microstate. So yeah, a black hole is basically not a pure state, or it's a coarse-grained state. We don't, at least in the classical gravity description, we don't know what its individual microstates are. So, but it's a collection of states within the parameters that we can measure in classical gravity is what we call a black hole. Any other question? Yeah, that was a good question. I should have drawn this picture. Okay, so I think that with that, I think we have sort of enough, I have said enough for you to follow all the things that you need in the next lectures, but it's important that, because maybe the information rate and because these are somewhat disconnected bits of information, that's the bigger problem. So you kind of have to familiarize yourself with them. So as I said, it's a skill set to kind of be able to navigate the information landscape so that you can get to what you want without getting bogged down in all the details that you don't, So there are two different skill sets in physics. So this is one of them. So the first part of the skill set was necessary for all the lectures before these 3 lectures, which is just to follow kind of things kind of sequentially. But here you kind of have to get an overall picture by picking some data here and there and kind of going with it. So from now, the next lecture onwards, hopefully things will be again more linear. All right? So, yeah, I think we can stop.